morning, friends and dear students. It gives me immense pleasure to be here again for my course Flight Mechanics. I will be discussing about the aircraft performance. I am Dr. Yagya Dutta Dwivedhi, professor from Institute of Aeronautical Engineering, Hyderabad, India. In today's discussion, I will be discussing about the topic numerical problems of atmosphere. Because if we talk about the aircraft performance, aircraft flies in the atmosphere and we should understand what is the atmosphere. In my previous classes, I have already discussed about layers of atmosphere, their variation of density, temperature and pressure as per the altitude, different layers of atmosphere, the variation of temperature in different layers are different with altitude. We have also discussed about lapse rate and some other things we have already done. Now I want to take some numericals on that topic. Most of the questions are taken from GATE examinations of flight mechanics. In today's class, I am going to take some points like finding the density variation as per the different altitude, finding the equivalent airspeed of the aircraft when aircraft is flying on the atmosphere, finding the density at altitude at different heights, what is the density of the atmosphere, finding the equivalent airspeed of the aircraft, in the previous classes also we have done some numericals to find out the coefficient of lift when different parameters are given and with the different conditions of flight. We have also find the time of climbing and other parameters, finding the velocity for a minimum drag, for the minimum range, for maximum range, maximum endurance and so on. We have already done some numericals. Then we have also find out the numericals, finding the aspect ratio of the aircraft wing. Then numerical finding the thrust to weight ratio. This we have already covered in my previous lectures. In today's, I am going to take some numericals. Numerical number 1. Considering the density and altitude of the base of the isothermal layer in the international standard atmosphere to be ρ1 and the h1 respectively, find the density variation with altitude in that layer which is governed by R, that is specific gas constant, T is the temperature, G naught is the acceleration due to gravity at the sea level. So these are the few things. We have to find out the relation between density ρ1 and h1 with respect to the R, T and G naught. This is our objective. So we have to see that how to find the relation between atmosphere, standard atmosphere, where the base layer is isothermal layer. So we know that the isothermal layer, if you see, this is this thing. Initially up to 11 kilometer, it is 11 kilometer. It is temperature. It is decreasing the temperature here. It is 288 and here from here to here it is isothermal. This is the isothermal. This is the A, this is the B and this is the C. So B and C is isothermal layer. So now we should see that the difference in the pressure is equal to minus rho G naught and dH, and we know that P is equal to rho RT. If you divide this dP by P, so minus rho G naught dH divided by rho RT, rho and rho is cancelled. So we will get here that dP by P is equal to minus G naught by RT into dH. Here it is shown that this is the base H1, rho 1, P1 and the T1, and we have to find out in this point what is the state of this temperature, pressure and this all the parameters. So now after this division of this into this, if this is the 1 and this you make as a 2, divide 1 by 2, so dP by P is equal to minus rho G naught dH, this one divided by this one. So now this is cancelled, so dP by P is equal to minus G naught by RT into dH. If we integrate from here T1, here T, here is a P and here is a rho, this is the condition. So from P1, from this to this integration, so P1 to P, dP by P is equal to minus G naught by RT H1 by H1 to H dH. So if we integrate this, we will get ln P by P1 is equal to minus G naught by RT H minus H1. Now if we make P by P1 and we will shift this log to this side, it will become e to the power minus G naught by RT H minus H1. So we have find out the relation between P and the P1. Now we have to find relation of density at point 1 and here star point here, so and star point here. So now we know that P by P1 is equal to rho RT by rho 1 RT1, because temperature is constant, it is a isothermal layer, so RT is cancelled. So P by P1 is equal to rho by rho 1. So we can write that rho by rho 1 is equal to e to the power G naught by RT H minus H1. So this is our relation, the density versus temperature, height and all we can find out by this way. So this is the relation which we have to find as per the given question. So here rho is actually, rho by rho 1 is directly proportional to the difference of the height. As you have, so here we can see that rho is equal to rho 1 H1 H minus H1. So it is directly proportional to the height. As much you increase the height, that much your rho will be decreasing. So that is the relation which we require to get in this solution. Hope it is very much clear. Now I will go for my next numerical number 2. A pitot tube mounted on the wing tip of an airplane at an altitude of 3 km measures pressure of 0.72 bar and outside ambient temperature is 268.66 Kelvin. Taking sea level condition as P is equal to 1.01 bar, temperature is equal to 288.16 Kelvin, density of this thing is 1.225 kg per meter cube, G is equal to 9.8 meter per second square. Gas constant R is equal to 287 joule per kg Kelvin. Assuming standard atmosphere, find the equivalent air speed of this airplane. So, if you see here that it is given that a pitot tube is mounted on the wingtip of an airplane at an altitude of 3 kilometers. So, the altitude is 3 kilometers. If we see here, up to 11 kilometer, this is the 11 kilometer, temperature here 28, it is falling, decreasing. So, and pressure is also here. So, the pressure is 0.72 bar and outside temperature is 268.66 Kelvin. At some 3 kilometer here, it is 3 kilometer. So, if you take here the sea level, that is sea level pressure is equal to P at sea level 1.01 bar, temperature at sea level TSL is equal to 288.16 Kelvin, rho is equal to 1.22 meters, 225 meter kg per meter cube, G is equal to 9.81 meter per second square, R is equal to 287 joule per kg Kelvin. These are given. So we have to find out the VE. VE is a equivalent air speed. This we have to find out. So this is also from GATE examination, and this we'll see in the next slide how to go ahead. So here solution of the problem is, given data, the pitot tube measures only total pressure, and the total pressure of this thing is given 0.72 bar at altitude of 3 kilometers. So given pressure PT3 is equal to at 3 kilometers, so it is, the subscript is 3. So 0.72 bar. So we will multiply by 10 to the power 5 to make it Newton per meter square or the Pascal. So 0.72 into 10 to the power 5 Pascal. Pressure at the sea level is 1.012 into 10 to the power 5 Pascal. Temperature at sea level is 288.16 Kelvin. Density at sea level, rho naught is equal to 1.225 kg per meter cube. Acceleration due to gravity at sea level is G naught is equal to 9.8 meter per second square. The gas constant R is given 287 joule per kg Kelvin. These are the parameters which are given. The T3 at 3 kilometer temperature is equal to T3 268.66 Kelvin, and the altitude H is equal to 3 kilometer 3000 meter. So these things are given, and we know that equivalent air speed is equal to true air speed under root rho 3 by rho naught. Rho 3 means at 3 kilometers what is the density and what is the rho naught at sea level. First we have to find the true air speed at 3 kilometers. So we know that P3 by PSL is equal to T3 by TSL to the power minus G naught by AR, where A is a lapse rate. This we can define A as a dt by dH, means temperature difference T3 minus TSL divided by H3 minus HSL. T3 is 268 here, it is mentioned here, 268.66 minus 288.16, which is given here, 288, this one at sea level. So 268.66 minus 288.16 divided by 3000 minus 0. So lapse rate we got is equal to minus 0.0065 Kelvin per meter. So this we got the means for every 1 meter the temperature is falling by 0.0065. So that one parameter which we have got from here. Now we will see the next that again P3 by PSL is equal to T3 by TSL minus G0 by AR. So now we have find out the AR. So P3 is equal to PSL into T3 by TSL to the power G0 by AR. We have find out, R is given, G0 is also given, all the parameters are given. So this atmospheric pressure at sea level is 1.01 into 10 to the power 5. T3 is equal to 268.66 divided by 288.16 to the power 9.81 divided by minus 0.065 into 287. So you will get the P3 is equal to, this is the value which you will get, that P3 is equal to 69871 Pascal. So this is the P3 we have got it. Now we have to find out the density. Density at 3 kilometer, that is called rho 3, and we know that P3 is equal to rho 3 or T3. So here from rho 3 is equal to P3 by R T3. Rho 3 is equal to P3 by R T3 and R P3 we have got it here. So 6969871 divided by R is equal to 287 into 268.66. So we will get density at 3 kilometer 0.9061 kg per meter cube. So now we got the P rho 3. You know this in this equation that EAS is equal to TAS into root rho 3 by, this is the rho 3 by rho naught. So now we got this, we have this. So now we have to see how to find out the equivalent airspeed. So here we know that equivalent airspeed is equal to true airspeed under root rho 3 by rho naught. So we can find out this under root rho 3 by rho naught, and this rho 3 we have just now obtained 0.9061 divided by 1.225. This we will get 0.86. This 0.86 we have got it. Now we have to find out the true airspeed, and we know that true airspeed is equal to under root 2 P naught minus P3 by rho 3. So here 2 P naught is equal to 0.72 minus 0.69871 divided by 0.9061. So there you will get this value, that true airspeed you will get 68.55 meter per second. This is the true air speed. So now it is very easy to find out the equivalent airspeed. Equivalent airspeed is equal to 0.86 into true airspeed, 0.86 into 68.55. So we will get 58.5954 meter per second. So the equivalent airspeed is 58.954, which is less than true air speed, which is less than true airspeed. So EAS is less than TAS. So this is the solution for this. The true airspeed of this given problem is 58.954 meter per second. So this is the another problem which we have solved now. I will go for the next problem, which is problem number 3 or numerical number 3. Assuming International Standard Atmosphere ISA at sea level conditions, temperature is equal to 288.16 Kelvin. Density rho naught is equal to 1.225 kg per meter cube. G is equal to 9.81 meter per second square. It is not S2, it is square. Gas constant R is equal to 287 joule per kg Kelvin. Find the density. We have to find this density at Leh Ladakh, which is at the altitude of 3005 meter from the sea level. Okay, so very interesting problem, a very practical problem also. So if you are in following the international standard atmosphere at sea level, temperature, density and the GR is given. Find the density at this much height. So the altitude of this system is given. This problem is given at Leh Ladakh is 3500 meter from mean sea level. So here given at sea level, temperature, pressure and the rho means temperature, pressure and the density, and the altitude of this thing is H is 3500 meter is given. We know that up to 11 kilometer it's troposphere where T is falling with altitude, that is called lapse rate A dt by dH, and this will be always less than that. So we know that with the relation that rho by rho SL is equal to T by TSL to the power G by lambda R minus 1. This is in power. So here rho SL is known, TSL is known, rho SL is known, this is known, TSL is known. We have to find out this rho. Find this rho. We have to find the T. So first we have to find T at 3500 meter. So we know that T is equal to TSL minus AHR. So here TSL is 288.16 minus lambda is equal to 0.0065 into H is equal to 3500. So you will get T is equal to you will get this value here. Okay. So now you can put this value here. So this rho is equal to rho SL T by TSL G by lambda R minus 1. So rho SL is 1.23, it is given, and from here T is equal to 288.16 minus 0.0065 into 3500 divided by T 28.16 to the power 9.81 divided by 0.0065 lambda into 287 minus 1. If you calculate this, we will get the density at 3500 meter is rho is equal to 0.836 kg per meter cube. So this is our answer, that at 3 kilometer we will have the density of the atmosphere will be 0.836 kg per meter cube. So I hope you are understanding. If any query, you are requested to send or give the comment. Also, you can send to my email. I will be sharing you at the last slide of this lecture. Now I am in numerical number 4. An airplane is in steady level flight with true airspeed is 50 meter per second. So here given the first thing is true airspeed is equal to 50 meter per second. The ambient air density, pressure, so rho naught is equal to 0.91 kg per meter cube and pressure is 70,000 Newton per meter square at sea level. So this is P naught at sea level. Find the equivalent airspeed of the airplane. So we have to find out EAS. Just before also we have discussed that EAS is equal to TAS rho by rho naught. This is our known equation. So here true airspeed is given, density rho naught is given, this is not given. So we have to find out first rho. What is the density? Pressure, density at sea level, find the equivalent airspeed. So let's see how we can proceed. So given data here, true airspeed Vt is 50 meter per second, rho is equal to 0.91 kg per meter cube, P is equal to 70,000 Newton per meter square, rho SL is equal to 1.225 kg per meter cube, P atmosphere is 1.01 into 10 to the power 5 Newton per meter square. So these things we can find out these things. So we know that VE is equal to TAS rho by rho SL. So this true airspeed is equal to VE divided by under root rho by rho SL. So here we have to find out the VE. So this VE is equal to true airspeed is 50 under root 0.91 divided by 1.225. So if you calculate this, we will get this value as 43.09 meter per second. So the equivalent airspeed is speed is 43.09 meter per second. This is the answer. In the next lecture, we will be again discussing about numerical related to the cruise flight. In that, we will be solving the problems for a maximum endurance condition, larger ground run, limit of load factor, find the wind loading, find the stall speed. So these 5 problems we are again going to solve in our next topic, next lecture. These are the references, that is Anderson J.D. Junior, Aircraft Performance and Design, International Edition, McGraw-Hill's, first edition, 1999. SL by ME, Aircraft Performance Theory and Practices, AIAA Education Series, AIAA. Any questions you are welcome to ask. You can like and subscribe this channel. Also, if anything you want to communicate, you can comment on my channel. Also, you can send to my mail ydwivedi@gmail.com. Please do like and subscribe this channel. Till then, goodbye. See you again. Thank you very much for listening and understanding the topic.
Like, share and subscribe. Hit the bell icon for more updates.